So next part, we'll go on to the column technology here, where I'll give you a brief overview of first what are uncoated columns, why we use them pretty much because of low cost. Coated columns are used with a higher cost associated and time, but that's done because of the prevention of absorption of the molecules here. Once it absorbs, it gets stuck, you create a imbalanced kind of a cavity, and also you can't separate your substrate. Next, we have packed columns. It's ready to apply some of chromatography techniques there, right? We fill with fluids. Next, also we have gel-filled columns. It's about using the size exclusion principle, the size sieving, right? But because of its size, in terms of the cavity, then it's easy to damage. Next, we have the dynamic sieving CE. It is easier to use than fixed gels. And lastly, we have the C on chip, and later on in this CM4242 lecture series, we also have a lab on chip series by Prof. Lee. This is really, as you know, on a chip means it's miniaturized, and something is more portable. You can bring out to the field work in the forest or the rivers if you want to test something quickly. So for uncoated columns, this is what you have seen, for many of these lectures here. This is your field silica capillary, in this case your 330 micron. Right, then of course inside, right, you have this capillary opening, 25 micron, very narrow, and this is a UV transparent outer coating for detections. So I have shared with you that in the class, your capillary, you can always burn it and you can see this transparent part, right, that light can pass through here. Now in this case, it's a bit special because you also have the polymer tubings, the PTFE, that's not UV transparent. Why is it important? Because if it's not transparent to the detection, in this case the UV detector, that means it's opaque, which means light can't pass through. We can't detect the difference in absorbance, which means there's no signal. It'll just be a flat line. Okay. For coated columns here, so they are coated within the column, right, to decrease the absorption of certain solid, for instance proteins. Why proteins? Because they have many locations for hydrogen bonding, and inside mostly is a lot of hydroxyl groups, so they bind very strongly via the ion dipole interactions or even very strong hydrogen bond. So what are some materials of coating we achieve inside the column here? One form is your polyethylene glycol, polyacrylamide with siloxane, SiO bond, right? And of course we have the silicon carbide bond silica, which is more pH stable than SiO, because in this case you have the labile hydrogen proton, right, from the silanol, but silicon carbide is a bit more stable. Now of course you have other liquid chromatography stationary phases, GC, that you have learned, right? You can try to apply this technique. And of course there's also one new one, which is your charge reverse coating, but also biopolymer. So I think this is better for you to see the structure. So first of all, how do you do coating material? We need to do some rinsing first, the washing using a strong base like potassium or sodium hydroxide within the silica, right? And after which, right, we open up this bond, and then we have some silanol and some siloxide ion. And of course, when we apply some drastic pH, in this case the more acidic medium, then we protonate all the silanol. After doing so, we introduce this polymer, right, a form of trimethyloxysilane, and then they will bind in this manner here. So now this part I'm putting my cursor over, it becomes the coating that will interact with analyte, right? Because before that, if you don't do this step, this coating, then your big proteins will just adsorb here, it just gets stuck and can't move when they're immobilized, right? One is you can't move, the other thing, it blocks the other substrate from going through. Now in this case, right, this is a polymer with this 600 molecular weight, right? It's intermediate kind of a polymer size. N is 13. This is a polymer repeat unit. So then you do a coating inside. So this is a bit more hydrophilic compared to the other one here. Next, we also have another form of coating. So now we have begin with silanol, and then of course we apply some organic chemistry material, your thionyl chloride, when your Cl replaces the OH and forms the SiCl bond here, okay, releasing some acidic gas. So you've got to pay attention, do it inside the fume hood, make sure you don't breathe in these toxic gases. And after which, right, this is more organic chemistry, right? When you apply this ethyl magnesium bromide, a form of Grignard reagent, your RMGX, if you remember, then it will form a very strong SiC bond here. They are very strong because of this same covalency in group 4, right? And with the release of this ionic salt here. Okay, and after which you have your alkene that's unsaturated, that's very prone to addition polymerization, and this is where you add your ethylene acrylamide, and of course it will polymerize. You see this chain elongation, right? And then you just coat the whole column here. Here, this is the electrophoregram by Professor Lee and his team, my seniors, about how we use the chitosan coated capillary, right, in the acidic medium here. So this is in this case not very prone to acidic medium in terms of variations, and of course we can separate the protein mixture. Now we have come to this part called the packed column for the CEC. There are actually many types of stationary phase particles developed for HPLC that we can also use for capillary electrophoresis chromatography here. So there are some kind of frites, right, which is a kind of ceramic material that we put inside there, to interact and to block it. Therefore, when it's not really like a vacuum, like a empty space. So there's need for some kind of pressure to push the liquid through this kind of packed particles there. Okay, and the term sintered means that it is there's just many holes, and normally we refer to some silicon oxides. Okay, there's some cavity. Make sure there's some kind of tunnels and channels for some liquid to go through here. Now for monolithic, right, this term is more of a materials chemistry. It just means that it's created in one piece, which means it's not like I take different parts and glue them together. So it's really created, uniformly, okay, through one kind of reaction. So we can also use that if you can grow some kind of a monolithic silicon oxide, then we require lower pressure to push the liquid through. And the reason is that monolithic is a bit more like a crystal structure. So when you talk about crystal growing, there's a kind of systematic bond formation, right? So it's not like it's randomly, like during combustion when you burn it, then you can have random formation of these holes and cavity. But when you grow a crystal, so there's a crystal structure that's very uniform, and that's why we call it monolithic. And therefore, if we have a monolithic structure, it requires lower pressure to push it through. The other kind of column is called the gel fill column. So we prepare with these bifunctional agents here, right? So it will bind chemically to the silanol group, right? And the other contains a second reactive group in the formation of some covalent bond with the gel. So it's more like one is attached to the wall of this column. The other side is to have extended reaction so that you can bind to the polymeric gel, because the gel is the one that you use to interface with your substrate. So this pore size of this polyacrylamide, in short, is called page, right? Gel is determined by the percentage T and percentage C. PAG, polyacrylamide. So this page, right, PAG, polyacrylamide gel electrophoresis, are characterized by two parameters. The total monomer concentration, we call it the percentage T in gram per 100 ml, and the weight percentage of the cross-linker, percentage C. So by varying these two parameters, right, the pore size of the gel can be optimized to yield the best separation and resolution for the proteins of interest. The percentage T indicates the relative pore size of the resulting polyacrylamide gel. So the higher the percentage T refers to a larger polymer to water ratio and on average smaller pores. Okay, next for gel fill columns here, right, we can prepare the gel without any bifunctional agent, and we can also use a low voltage, less than 0.3 kilovolt per cm applications. Now there's a few kinds of page we can use here. First is the non-cross-link page, which is easy to empty and refill because of a lower cross-link means that there's not many covalent bonds within, which means you can always wash it out quite easily and refill it. And that also means the lower resolving power because they're not cross-linked. However, when you want to use Agua rose gel, this allows the UV detection at a shorter wavelength, right, closer to the UV side here, the more powerful, but it's less stable. Okay, no matter what kind of gels we are going to use here for the page, for gel fill columns here, it follows this rule about the resolution and efficiency, dependent on the migration time and the standard width for the single pit. This is how we calculate which one has a better resolution. For the polymer matrices of CGE, right? So again, we have a different kinds of polymer. If we use cross-linked polymers like this polyacrylamide, the page, right? These are specific applications. The analyte could be oligonucleotides, DNA sequencing, or native SDS-bound proteins. If you're going to use something more linear polymer, like a page, but a polyvinyl alcohol PVA, dextrin, this is to apply for analysis of these restriction fragments or oligonucleotides, DNA sequencing, and proteins. So you see there's actually some overlap between these applications. So again, you have to try and see depending on the availability of the polymer which CGE you can use. Now for agarose, it's primarily for the restriction fragments and proteins there. For dynamic sieving of CE, right? So we recall in the previous slides we talked about how we apply these size sieving solutions because they have different size cavity, and we are going to apply some soluble linear polymer like a methyl cellulose or polyethylene glycol here. And because it is easy to remove them, right, from the column compared to the gel, because their solution form, that means they're more fluid and less viscous, so easy to change and remove it and recycle this column. Now, but the viscosity of solution, right, pay attention, it shouldn't be too high so that you can remove it, pumping pressure, and exchange it. Of course, due to its lower viscosity, it has a lower efficiency than gel-filled columns because it's a bit less stable. Your agarose or these gel-filled are immobilized, so you have some kind of a consistent cavity. Okay. Here you see a capillary array with a shield flow cuvette. You see this 4 here, right? 4 channels. This is a snapshot of this 96 capillary detected simultaneously. So imagine 4, how many are there? Right, 4 multiplied by 24, right? That's how you get 96 here. So here we have this laser beam across here, right? It's scanned at the same time. We are optimizing the refractive index of the shield flow liquid to ensure that this laser beam passes through all the capillaries. It doesn't miss out. Okay, 96 capillaries in one row here. It's a bit hard. But as a close-up, we can see this is very precise engineering. So the ray will pass through all of them. Okay, the 96 well plate containing the sample, so you can save time by running concurrently. This is again a zoom out version. So we can pipette down all these 96 capillary tubes for the size of comparison. And this is even zoom out bigger. I see so many capillary here, and this is the CE. There's one in Professor Lee's group here, so do drop by if you're allowed to come in to do some research work. There's this optical detection system, right, that shine the light, focus to the tube because they're very narrow, and it can detect the amount and the color of the emitted light. So this is one of the close-up look. We call it a gooey mixture, right? Very sticky. And you see that this stretches between the yellow tip, right, and the vial, right, after each run.